Look at this city. Millions of people, millions of lights, every road, every building, every life, spread out across hundreds of square kilometers. Now imagine an object smaller than this city. Not a building, not a stadium. An object the size of a city block, 20 kilometers across. Now imagine that object is heavier than the sun. Not a little heavier, not twice as heavy, heavier than 500,000 Earths stacked on top of each other. All of that mass compressed into something you could drive across in under a minute. This is not science fiction. This object exists right now in our galaxy. It is spinning 716 times per second. The equator of its surface is moving at 1/5 the speed of light. And it is not flying apart, because the gravity holding it together is 200 billion times stronger than what holds you to the ground right now. 1 teaspoon of its material would weigh 1 billion tons on Earth. 1 teaspoon. The entire ocean of Earth compressed into something you could hold in your hand, and then compressed 1 billion times further. Its surface is 10 billion times harder than steel. Its crust is a perfect crystal. The tallest mountain on its surface is 5 centimeters high, because gravity will not allow anything taller to exist. And its core temperature is 1 trillion degrees. When two of these objects collide, and they do collide, they release more energy in 1 second than our sun will produce in its entire 10 billion year lifetime. And from that collision reigns something extraordinary: gold. Every piece of gold on Earth, every wedding ring, every coin, every gram of gold ever mined in all of human history was forged in the collision of two of these objects, billions of years before Earth existed. The violence that created your jewelry is the most extreme event the universe is capable of producing without creating a new Big Bang. This is a neutron star, and what it does to the universe around it, and what would happen if one came anywhere near us, is more terrifying, more beautiful, and more impossibly extreme than anything else the cosmos has ever produced. To understand what a neutron star is, you first need to watch something die. Not a small death, the largest, most violent death the universe performs. A supernova. A star 20 times the mass of our sun has been burning for 10 million years. It has been fusing hydrogen into helium, helium into carbon, carbon into oxygen, all the way down the periodic table, building heavier and heavier elements inside its core, until it reaches iron. Iron is the universe's dead end. You cannot get energy by fusing iron. You cannot get energy by splitting it. Iron is where fusion stops. And when enough iron builds up in the core, in less than a second, everything changes. The core collapses. Not slowly, not gradually. At 1/4 the speed of light, the core, the size of Earth, implodes to the size of a city in 0.1 seconds. The outer layers of the star, still burning, still fusing, have no idea this is happening beneath them. For a fraction of a second, the star doesn't know it's already dead. Then the shockwave hits. The collapsed core bounces, and the rebound shockwave blasts the outer layers outward at 30,000 kilometers per second. The star explodes. For weeks, it outshines an entire galaxy of 200 billion stars. And at the center of that explosion, something is left behind. The collapsed core did not become a black hole, not this time. The mass was not quite enough. Instead, gravity compressed the protons and electrons of the core together into neutrons, and the neutrons packed against each other so tightly that they created a new kind of pressure: neutron degeneracy pressure, the quantum mechanical resistance of matter that has been pushed to its absolute limit. The result is a neutron star, born in fire, made of compressed death. In its first moments, it is the hottest thing in the universe, 100 billion degrees. It is spinning hundreds of times per second, and it is already firing twin beams of radiation from its magnetic poles into space, a lighthouse that will sweep the galaxy for millions of years. This is what's left when a star too massive to live, but not massive enough to become a black hole, dies. A city-sized sphere of compressed neutrons, the most extreme stable object the laws of physics permit to exist. Let's talk about what this object actually is. Because dense doesn't cover it, massive doesn't cover it, we need new language. The density of a neutron star is nuclear density, the density of an atomic nucleus. Every neutron packed against every other neutron with no space between them. This is the densest form of matter that can exist without collapsing into a black hole. If you took the entire human population of Earth, all 8 billion people, and compressed them to neutron star density, they would fit inside a space smaller than a single proton. The gravity on the surface is 200 billion times stronger than Earth's. If you fell toward a neutron star from 1,000 kilometers away, you would reach the surface traveling at 100,000 kilometers per second. That is 1/3 the speed of light. And when you hit, the energy released would equal 10,000 nuclear weapons detonating simultaneously. The neutron star would not notice. The magnetic field of a typical neutron star is 1 trillion times stronger than Earth's, strong enough to rip the electrons off atoms at a distance of 1,000 kilometers. But some neutron stars have magnetic fields 1,000 times stronger than that. They are called magnetars, and they are perhaps the most terrifying objects in the known universe. On December 27, 2004, a magnetar 50,000 light-years away experienced a starquake, its crust cracking under the stress of its own magnetic field. In 0.2 seconds, it released more energy than our Sun produces in 300,000 years. Even from 50,000 light-years away, nearly crossing the entire Milky Way, the burst was powerful enough to measurably compress Earth's ionosphere. Think about that distance, 50,000 light-years. If you drove at highway speed, it would take 500 billion years to get there, and we still felt it. If that magnetar had been 10 light-years away instead of 50,000, the same distance as some of our nearest stellar neighbors, the burst would have stripped our atmosphere and ended life on Earth in under a minute. This is the scale of what a neutron star is capable of without even trying, without moving, without approaching us, just cracking slightly under its own internal stress from across the galaxy and nearly reaching us. Not all neutron stars are the same. The ones we detect most easily are called pulsars, rotating neutron stars whose magnetic poles happen to point toward Earth, sweeping us with their radiation beam like a lighthouse beam sweeping a coast. The first pulsar was discovered in 1967 by a 24-year-old PhD student named Jocelyn Bell. The signal was so perfectly regular, a pulse every 1.3373 seconds, precise to the microsecond, that the research team briefly labeled it LGM1, Little Green Men 1. They genuinely considered for a moment that it might be an alien transmission. The universe had created something so regular, so mechanical, so precise, that it looked like technology. It wasn't alien. It was just physics pushed to its limit. Some pulsars spin 700 times per second. They are called millisecond pulsars, and they are the most accurate natural clocks in the universe. The best of them keep time to within 1 second over 200 million years. For comparison, the best atomic clocks humans have ever built lose a second every 300 million years. We are almost matching the precision of a dead, spinning, city-sized ball of compressed neutrons. Almost. When two neutron stars orbit each other, and we have found pairs of them, they are slowly spiraling inward. Every orbit, they lose a tiny amount of energy to gravitational waves, ripples in space-time spreading outward at the speed of light. In 1974, Russell Hulse and Joseph Taylor discovered such a pair. Over years of observation, the orbital decay matched Einstein's predictions for gravitational wave energy loss to within 0.2%. That measurement won a Nobel Prize. Two neutron stars, dying together in slow motion across millions of years, confirmed a prediction from 1916. Now we come to the moment everything changes: the merger. When two neutron stars have been spiraling toward each other for hundreds of millions of years, they finally close the last few kilometers in a fraction of a second and collide. The event that follows is called a kilonova. It is named for the fact that it is approximately 1,000 times brighter than a standard supernova. In the first millisecond, more energy is released than the Sun will produce in 10 billion years. Gravitational waves ripple outward through space-time, and neutron-rich material, matter so dense that neutrons are practically touching, blasts outward at 1/3 the speed of light. In that material, something extraordinary happens. The conditions are exactly right for a process called rapid neutron capture, the R process. Atomic nuclei capture neutrons faster than they can decay, and in this environment, in this brief, violent moment, the universe manufactures heavy elements: gold, platinum, iridium, silver, uranium, thorium. Every element heavier than iron that could not be made in a star's core, all of it forged here in the collision of two dead stars. On August 17, 2017, we watched it happen. Gravitational wave detectors on Earth, LIGO in the United States, Virgo in Italy, registered the merger of two neutron stars 130 million light-years away. 70 observatories around the world pivoted to watch the optical afterglow. The event was designated GW170817, and within its fading glow, spectroscopes confirmed it: strontium, gold, platinum, the heavy elements, appearing in real time as the kilonova cooled. We watched the universe make gold. The gold in your ring, the gold in your phone, the gold in every vault and every crown and every treasure in human history. All of it, every atom, forged in the collision of two neutron stars somewhere in the universe before the Earth existed. You are wearing a piece of the most violent event the universe produces. There are an estimated 1 billion neutron stars in the Milky Way. Most of them are cold, dark, and completely undetectable. No pulsar beam aimed at us, no accretion disk, just an invisible sphere of compressed matter drifting through the galaxy. We would not see one coming. The first sign would not be the neutron star itself, it would be comets, thousands of them, all at once. Beginning long inward falls from the Oort cloud, the shell of icy bodies at the edge of the solar system, their paths disturbed by a gravitational influence we could not immediately identify. Then Pluto's orbit would begin to wobble, then Neptune's moons, then Saturn's rings, those perfect, iconic arcs, would begin to develop gaps and streams as the gravitational resonance disrupted the careful balance that has held them in place for 4 billion years. Saturn's rings, gone within months. Jupiter's moons, in orbital resonance for billions of years, would begin to shift. Io's volcanism would intensify to a level never seen. Europa's ice would crack. The carefully ordered outer solar system, the structure we were born into, would begin to come apart. And then, Earth. The tides first. Ocean levels across the planet rising and falling in patterns our planet has never experienced. Day length growing erratic. The crust under increasing stress. Earthquakes and volcanic activity rising globally. Not from impact, not from radiation, not yet. Just from gravity. Just from the fact that something impossibly massive is getting closer. A neutron star passing within 1 light-year of Earth would not need to touch us to end us. The gravitational disruption to our orbit over centuries would be enough. The comet bombardment triggered by the disturbed Oort cloud would be enough. The atmospheric stripping from its radiation, if it were a pulsar, would be enough. Any one of a dozen mechanisms, all of them operating simultaneously, would be enough. The good news, we have mapped the nearest neutron stars. The closest confirmed one is 400 light-years away. That is a safe distance, for now. What happens to a neutron star in the end? It cools. Over billions of years, its surface temperature drops. Its spin slows. The pulsar beam fades to silence. Eventually, the neutron star becomes a cold, dark, perfectly crystalline sphere, the largest diamond the universe can make, drifting invisible and eternal through the galaxy. In the far future, trillions of years from now, when the last stars have burned out and the galaxy has gone dark, the neutron stars will still be there. Cold, silent, invisible, but there. And some of them, the ones in binary systems, still spiraling toward each other in the dark, will still be falling toward their merger. Even in a dead universe, with no stars left to light the collision, two neutron stars will find each other, merge, and for one brief moment produce a kilonova. One flash of gold light in an otherwise completely black universe. The last act of creation in a cosmos that has otherwise ended. You are made of star stuff. Carl Sagan was right about that. But more specifically, the gold in your body, the heavy elements that make you work, the atoms of every precious metal in human civilization, you are made of neutron star stuff. Forged in a collision so violent it outshines a galaxy, carried across billions of light-years, incorporated into a cloud that became our sun, our Earth, and eventually, you. The most extreme object the universe allows to exist, smaller than a city, heavier than the sun, spinning 716 times per second, harder than anything, hotter than anything, more magnetic than anything, made you. And somewhere in the Milky Way right now, 1 billion of them are drifting in the dark, waiting.